Hello everyone, we are Group 9 and today we present our project Anatomy Aware Denoising Framework for Low Dose CT at Variable Dosages. We will walk through our data creation process, proposed architectures, implementation details, and end with qualitative, quantitative, and ablation results. CT scans offer excellent diagnostic details but expose patients to radiation. Lowering the dose reduces the risk but introduces noise, which hides the subtle anatomical features. Our goal is to develop a deep learning framework that restores near normal dose CT quality across multiple dosage levels 10 to 70% while preserving fine edges and textures. We also emphasize anatomy aware validation, ensuring radiomic features and structures remain stable. We generate realistic LDCT using physics-based noise stimulation. For Lodopave, we convert images to projections, add Poisson short noise based on dose, and reconstruct using FVP. For AAPM, we noise the projection counts directly before reconstruction. This gives us paired LDCT and DCT datasets at 10, 25, 50, and 70% dose levels. It is shown here for your visual reference. Now let's have a look into the code for dataset preparation. First is the code for preparing data pairs from AAPM dataset. Here we have used Astra Toolbox. It allows us to stimulate a CT scanner and reconstruct CT images from projection data. First is the load decom series function. This function loads a folder of CT decom slices, orders them correctly, converts pixel values to Hounsfield unit, and stores both image and spatial information for further processing. Next is the HU2 mu function. This function convert the HU to linear attenuation coefficients mu because CT projection and reconstruction physics operate on attenuation coefficients, not on HU values. This is the Astra forward fan flat function. So this is the function where we are stimulating fan flat CT scan by forward projecting a mu image into a clean sinogram using realistic CT geometry. Next is the Astra FVP FanFat function. This is the function where we reconstructs a CT image from a noisy sinogram using fan beam filter back projection. Here is the add noise function, add Poisson noise function. So this is the main core of our dataset preparation, where we add the noise into our data to prepare LDCT. Here we are adding noise to the sinogram to stimulate real life LDCT CT scans. It is important that instead of directly injecting noise into images, we must add noise to the sinograms and then reconstruct. Because in real life images, the noise arises before the reconstruction from the randomness in the photon detection. And here is our code for generating dataset pairs from Lodopair dataset. Here we have generated the datasets, but we haven't used these generated pairs in our training. So here is the code for your reference. Here we can see different LDCT images that we have generated at different dosage levels: 10%, 20%, 50%, and 70%. These are for AAPM dataset. We can clearly see that lower dosage levels have blurry features and grainy texture, while higher dosage gives a more clear image. We have generated 5,936 images with these different dosage levels at for AAPM dataset. Now the same I am showing for Lodopav LDCT images at different dosage levels, but the images are not of good quality as compared to AAPM. So we haven't used this dataset for training purpose. Here images are of dimension 384 cross 384, but in case of AAPM we have this for 512 by 512. So we find it better option to use AAPM dataset for training purpose. However, Lodopav dataset have 17,791 images.
Now onto the proposed solution. So our baseline architecture uses a teacher-student setup that a teacher encoder decoder is trained only on normal dose CT to learn clean anatomical representation. The student encoder is given LDCTs and learn to map noisy images to the same latent space as of teacher. Both share the same decoder as you can see from our diagram. So the student relies on teacher knowledge for reconstruction. Our losses include the L1 plus SSIM loss for reconstruction quality and latent L2 loss, which is shown in the green part here. Now on to the proposed improvements. So firstly, the improvement that we suggest is teacher-student latent distillation as well as feature map distillation, forcing LDCT latents to match the NDCT latent distribution. The second one is improvement in loss functions, which is structural and perceptual constraints. So firstly, this we introduced edge loss which is just Sobel gradient consistency across all the pixels. The second one is multi-scale structural similarity loss, which is just structural similarity loss over multiple scales of the images. And the third one is perceptual loss, which we compute using some pre-trained vision model. In our case, we used VGG model on both denoised image as well as NDCT image, and then computed L2 loss over their features. And this is feature distillation, which we used for student and teacher feature maps, and then we try to reduce it. So uh, next chapter is implementation. So these are all the aspects that I talked about. Another one is dose conditioning. We also gave our student encoder the information about dose, like which LDCT dose is given to the student encoder. So as we can see in this pipeline, we provided the dose information by using MLP and then giving it to encoder, so that our encoder knows by how much does it have to denoise the LDCT image. In this, I told you that we used VGG19 to reduce the perceptual loss also. These are all the losses that I talked about. So let me show you our implementation. So so this was our baseline training code. So in that we use this seed so that we can reproduce all the results. Save PNG is just a function to save the images. So the laws that we used were SSIM and the doses allowed were these, and this was our data loader. Then this was our data loader, and we just use convolution network in our encoder as well as decoder. This was just based on convolution, and then this we trained our model. So this was just a baseline model based on a convolution architecture. So and now with improved uh, and this was all the metrics that we got. And for NAFnet, we applied all the improvements, and so we can see in this code. This was our data loader. So SFT layer, in this we use SFT layer to inject those information inside all the layers in student encoder. Simple gate is a function. So firstly, let me explain it. So so our inference pipeline only uses student encoder and decoder. We do not require teacher encoder at that time. So it is a single pass denoising process. This was our encoder architecture of improved model. So we use NAFnet based architecture. So this was our NAFnet encoder. Firstly, there is convolution head, down one, down two. This was downsampling layers, and then NAF block. So this was our NAF block, which we directly implemented in our project, just with one change that we removed the skip connections between encoder directly to decoder, because that can pass on the noisy features also. So that's why we removed these skip connections from encoder to decoder. Rest all the this block is same, which uses simple gate and simple or and channel attention. So I'll show it in my code. Yeah. So the SFT layer was to inject this dose information. Simple gate is used in NAF block. So this was our NAF block. Yeah. So these were permute functions and the convolution layers. This one was simple gate function, and then this was simple channel attention, which used. And this was our residual connection with beta is a learnable parameter, which the model will learn while training. And then this was another layer with residual connection with in gamma, which the model will learn. Now we have also implemented, so this was our NAF block, and now we also implemented conditional NAF block, because in student we also gave the dose information, so that's why we have to just add an SFT layer to inject our dose. Rest all is the same. So this will check if it is student, then it will inject the dose information using an MLP. Rest all are both these codes are same. Now this is the decoder, which is just the reverse of what we are doing in encoder. Now all these laws that we used. First one is SSIM. Use SSIM library for this loss. Second one is perceptual loss. So we used VGG19 model to extract features from our denoised image and NDCT, and then we applied L2 loss over both of these extracted features. So the other one is gradient loss. This is just a Sobel gradient across all our convoluted across all the across image, and then uh, in added in try to we try to minimize the L1 loss across the gradient. Now this was our training functions. So this was our evaluation function. Just printed all these metrics. Now this was our teacher training code. So during teacher training, we just use SSIM and L1 because other losses were required only during student training. So we initialized our encoder and decoder, and we also used a cosine annealing and LMW optimizer. So we trained our encoder and decoder, and then we saved as these PT files. Then while training our student, we froze them. As we can see from here, we froze our teacher as well as decoder so that we can try to mimic the latent distribution of our encoder. So now uh, this is our distillation weight parameter of latent distillation as well as feature map distillation. Now we have initialized all these losses, VGG, MSSIM gradient. Uh, this was L1 and alpha SSIM. So now we trained our student encoder. These are all the arguments. Almost everything is fixed. We trained our teacher for 100 epochs and student for 150 epochs with batch size of 8 and learning rate of 2 into 10 raised per minus 4. And we used seed 1, 2, 3, 4 for reproducible results. And so this was our training code. And now results and analysis will Rohan will continue this.
So, as of my portion, I'll be covering the results and analysis and at the final conclusion part. So, let's begin with that. So, here, topic 4 results and analysis, including the quantitative, qualitative, and evaluation studies. So, first of all, the quantitative analysis part. Our model shows a consistent improvement across all the dose levels, and we achieve around 40 to 44 decibel PSNR and SSIM above 0.94, with some samples exceeding to 46 to 47 decibels as well. The teacher loss converges quickly, forming a clean latent space, while the student loss steadily decreases and stabilizes, showing the successful distillation. So before going to the key insights, first look at from our code that how do we draw these results and especially the plots. So here it comes. First of all, for the quantitative results, we'll go to the NAFNet, which was the best performing model. So here I'll go into the ADL results and then NAFNet. In this NAFNet, I'll go to the evaluate NAFNet, and here in the main part, I have been given the argument for extracting it. I'll use this Python evaluate nafnet.py. Here the Mayo root, and it's the pathway to our dataset from here. And yeah, from LDCT pairs, and from then and the weights directory, I have gained it from the runs and that nafnet and student. Here, the thing to focus is that in the ADL results there will be runs, and in this nafnet there will be student, including the student encoder and decoder, and these two are only important for the inference portion. So we'll run this and try to get the metrics. So yes, we have got our metrics, and we can see this exactly matches with what we got here. And in the exact same way, we can get the other matrices as well for the baseline. From here, we can get the argument for the baseline, evaluate baseline.py, and from the runs, we can get the baseline student. From here, we can get the weights directly, and in the exact same way, we can get the its matrix as well. Now we'll move upon how we gather the plot. So for this, I have opened a new terminal where I have activated my conda, which I named Nari, and now TensorBoard log directory runs. Entering that, yeah. So I will get a link TensorBoard. Yes.
this, we will go to scalars, smoothing we can set. And now if we only want to see the NAFNet, the final one in the quantitative analysis, so we'll check only NAFNet student and NAFNet teacher. Rest we'll keep off. So this way we have got the student loss as well as here the teacher loss. Yeah, so let's move on to our slides again. Now I have shown you how we gathered the matrices as well as the plots. So let's move ahead. The key insights portion. So we saw that the improvements are strongest at extremely low doses, like 10 to 25%, and high doses still improve without overfitting. The stable student convergence shows that the model effectively learns the noise invariant structure representation. Now let's move on to the ablation studies. We compared NAFNet, ResNet, and UNet architectures. All have similar parameter counts, making comparisons valid. First of all, NAFNet performs best as its gated depth-wise blocks preserve the fine structure better than ResNet or UNet. UNet skip connections sometimes reintroduce noise, and ResNet lacks gating and thus smoothens the small features. Loss curves confirm NAFNet converges faster and reaches the lowest steady state loss. But we can see here the the ablation studies results. Now I can show you one of them, that how do we gather those matrices. Again, I will show you. So first of all, we'll go to the ADL results, in which now I will go to the ResNet and then evaluate ResNet. For this, the argument will be in the main part. Yeah, so the argument is here. I'll go again. Python evaluate resnet.py. Main root I have to change. I have not to change this one because the data set is same, and the weights directory I have to change. So here the ADL students. Okay, so first of all, the change I have to do is in the results. Then yeah, so now we can proceed. So this code also generates the evaluation images, as we are feeding to it save images. It will save the evaluation images as well. It will help us. And in the exact same way, we can get all the 5 variants of the evaluation, namely NAFNet with NODOS knowledge, with DOS knowledge, and with RedImage, with ResNet, and with UNit. I have shown two of them to you, NAFNet and ResNet. And in the exact same way, we can gather the evaluation metrics for all. Now I can show you the tensor board again, in which there were the plots. And here we can see we can open all of them, the NAFNet, RedImage, teacher, student, and then NAFNet nodos. And yeah, so if you want to see all 5, so we can see by here. And if you want to generate the exactly same as we shown in the PPT, so it was generated from the top, the main 3 ones, namely the ResNet, UNet, and the NAFNet. So if we want to see that one, we'll remove the NAFNet RedImage and NAFNet nodos. So this was the graph, and this was exactly same what we gathered from what we showed in our PPT. So yes, this is also matching. Now we'll move on to the next slides. So they are the key insights, and I have told which was the best performing, the NAFNet, and the worst performing was UNit. So now we'll come to the qualitative analysis demonstration. So we'll see from where we have gathered them. So these were the images which we took as sample. Like we can show this one, the at 25 dose per dose, the third sample, or at second sample from dose 70%. So we have shared some snippets, some clips from these eval images only. Now we can move upon the 10% dose. The noise is significantly reduced, but minor over smoothing remains. By 25 and 50%, the dose edges and textures are very well preserved. And at the 70%, the reconstructed images are nearly identical to NDCT with minimal residual noise. And as you can see, with naked eyes, we cannot even differentiate between them at high doses, especially. So let's move upon to the final conclusion and future work. So the conclusion, our anatomy aware dose adaptive teacher student framework consistently reconstructs the DCT image qualities across the dose levels. Now FNET's gated design and our multi-part loss ensure excellent structural preservation, outperforming the ResNet and UNit baselines. And we plan to integrate Mamba or transformer-based global context modules, extend to multimodal or multi-anatomy datasets, and explore uncertainty estimation and model compression for the real-time clinical use. Thank you very much. Yeah, from good night. Yeah.